every 7th ticket is a golden ticket, 7, 14, 21, 28. But some numbers are already claimed. Which golden ticket is the first one still free? Given an array of numbers and a target multiplier k, find the smallest positive number that's a multiple of k and doesn't appear anywhere in the array. In other words, look through k, 2 times k, 3 times k, and so on, and return the first one you don't find in the list. This is smallest missing multiple of k on LeetCode. I'm Kai. This is Fun with Learning Technology. Let's go find that missing multiple. You get a list of numbers called nums and an integer k. A multiple of k is just any positive number you reach by adding k to itself over and over, k, 2k, 3k, and so on. Somewhere in that endless list of multiples, one is missing from nums, and your job is to return the smallest one that's missing. Take nums as 8, 2, 3, 4, 6 with k equal to 2. Check 2, it's in there. Check 4, check 6, check 8, all in there too. Check 10 and it's nowhere in nums, that's our answer. Nums holds up to 100 numbers, each between 1 and 100, and k is also between 1 and 100. Small, but a naive check still means rescanning the list for every multiple you try. The obvious move, start at k, check if it's in the array. Not there, try 2k. Still there, try 3k. Each check means scanning the whole array again. That's the slow part. If the array has n numbers and the answer is the mth multiple, you're doing m scans of n elements each. In the worst case, that's quarter tick. And interviewers will ask you to do better. Start at k, then 2k, then 3k. Each one flashes red if it's in the set. Claimed. The first one that flashes green, not in the set, is your answer. There are only n claimed numbers total. Each claimed number can block at most one multiple of k. So by the n plus 1 people, you're guaranteed a free one. Here's the whole thing together. We turn nums into a set called claimed, so checking membership is instant. Then multiple starts at k. As long as multiple is sitting inside claimed, we add k and try the next one. The while loop stops the first time multiple isn't in the set, and we return exactly that value. Building the set costs 1 pass, big O of n. Each multiple check is now big O of 1, not another full scan. Total time comes out to big O of n, not the big O of n squared we had before. Build the set once, walk k, 2k, 3k, checking each in constant time. Stop at the first free one. Answer delivered instantly. That's the move anytime you're testing many values against a fixed collection. Trade the repeated scans for one hash set, and every check after that is free. The only part worth pointing at twice is that while loop, it isn't scanning anything. It's just asking the set a yes or no question and stepping forward by k until it finally gets a no. Time is big O of n for building the set, plus however many multiples we check, which never outgrows the array by much, so it's linear overall. Space is linear too, just the set holding every value. Worth keeping past this problem. Anytime you're scanning a list just to ask, is this in here? That's the signal to build a set first instead. Give it a second before I give it away. Both are technically OS1 per check. The real win is the set. Lets us walk missing numbers directly instead of rescanning the whole array for every candidate. Say k is 5 and every multiple up to 100 shows up except 95. Does our walking approach ever fail to find that gap? Pause and think it through. Here comes the answer. No, it can't miss it. We walk multiples strictly in increasing order. So the first gap we hit is guaranteed to be the smallest missing one. We just solved smallest missing multiple of k. Find the smallest positive multiple of k that isn't already in the array. The trick was dropping every value into a hash set, then walking k, 2k, 3k until we hit one that's missing. That lookup makes each check a 1, so the whole thing runs in own time with own space.